So anybody here ever performed a study in SKM, ETAP, Easy Power? Those are the electrical engineering softwares that a person like myself would use when performing the analysis. I actually have licenses to all three softwares and very familiar with all three because it really depends on what the client is using. We don't want to make them change, especially if they have their whole vessel or their whole facility modeled in one software, and then, you know, as a company, we're stuck using a different kind of software. We want to be able to, you know.
What's this software?
It's ETAP, Operational Technology. It's electrical analysis software for performing short circuit analysis, coordination studies, and arc flash studies. We also use SKM, Power Tools for Windows, and then Easy Power is another one. There's another, well, there's a few others out there, but another one is EDSA, and then one that they use overseas is Digsilent. So we really don't have any requests to use those kinds of softwares very much, so we just stick with the top three that we're normally requested to use. Before I even jump into this, I think one of the big things I need to discuss is, now that we're here in the new year and we're in 2018, it's the changes that have occurred in the 2018 70E. There's actually quite a bit, just as there has been every other, you know, 3-year revision cycle of the 70E. I think one of the largest ones is going from joules to calories per centimeter squared. You know, all the clothing that you purchase for working on live electrical equipment is now rated in calories per centimeter squared, but the models that were used inside of the standards were always based on joules. So that's one thing that you do need to take note of, and the units of measure are actually quite different. Another thing that has been changed is more of a transition to a risk assessment versus actually, I shouldn't say more of a risk assessment, but they're focusing a lot more on the risk assessment rather than actually pushing people to do more of a calculated study. You know, it is my personal and conservative belief that using the risk assessment method and tables that are listed there in the 70E can actually be quite confusing to the people that are actually working on the equipment. They want you to know the short circuit of at the point that you're working on, or that, you know, panel board or switch board that you're working on. They want you to know how fast do those devices operate. And a regular technician isn't going to be able to tell you whether, you know, they're about to open up the doors to a 3-cycle breaker, a 5-cycle breaker, and how fast the relay is going to operate there. Or it might just be a thermal mag breaker that they're working on, but normally they can't tell you that. So trying to have them go to the tables and use those to find out what PPE they need to wear, I think that's really not the approach that I'm most comfortable with. If, you know, by performing the studies, we're actually taking the amount of fault current that you have at the starting point, whether it be a utility connection or generators. We take that into account. We take into account the cable lengths, cable sizes, because that all affects the impedance of the system, and then how strong that fault is going to be at points downstream of those utility sources. And we also take into account the loads, the motor sizes. One thing that we always do is we model all the motor loads in the system, and that's because whenever there's a fault in the system, all the motors that you have in the system are actually acting as generators. So all those motors are contributing back to that fault current. So that's something that you want to keep in mind if anybody ever does, you know, perform a study for you, that they're modeling it to that level of detail. One of the other things that they did remove, which I'm not very comfortable with, in the 2018 70E is the dangerous 40 cals per centimeter squared. They're no longer, since they're pushing you more towards doing a risk assessment rather than the calculations, it's almost telling somebody that where we used to consider the 40 cal the cutoff line where you shouldn't work on the equipment, it's almost saying that if you do calculate something more than that 40 calories, go ahead and wear a 100 cal arc flash suit and you'll still be safe. But as Paul said, that doesn't protect you, that clothing does not protect you from the shrapnel, from becoming blind, from becoming deaf, from being thrown across, or blown away from the switchgear onto a wall. It doesn't protect you from any of that. All it's doing, all that clothing is doing is actually protecting you from a second-degree burn. So keep that in mind also. Another change that they made in the 70E is there used to be some confusion or people not being able to understand the mathematical symbols that are used in the 70E, so now they've gone to more of a verbal style in the standard. So like the greater than symbol, which used to be this way, is now the words greater than. So it makes it better for those who are not mathematically inclined but still trying to keep their people safe and keep themselves safe. And a larger focus has been put on 1.2 calories per centimeter squared, because that really is your arc flash boundary. That unqualified person should not be entering within that limit. Once you've performed your arc flash calculations, you should not be entering within a zone where there's greater than 1.2 calories per centimeter squared, especially if you're an unqualified person. And the definition of a qualified person is very important to understand, because in the court of law, they will use it word for word. Basically, what it's saying is that you have been trained or educated in the construction and the modeling, construction and installation of that equipment. So, and the operation of that equipment. So I can't say that there's too many people out there that can meet all of that criteria all the time. So really what it boils down to is not too many people can actually work on that equipment while it's live. So just be careful, with that terminology in the 70E. All right, so let's talk about 12 reasons why you need an arc flash analysis. OSHA, we've said that many times. They're the ones that actually require it or mandate it. NFPA 70, in the older versions, they actually only had a little snippet in there about actually requiring arc flash stickers, and those are just standards. There's nobody that's going to come in from those agencies and fine you, but OSHA does actually, absorb those standards into their toolkit, and they're the ones that can fine you based on those standards because they have adopted those. And one of the biggest things is, how does an arc flash study, benefit me? When we're dealing with the bean counters, you have a large facility and all of a sudden you're trying to give them a proposal for tens of thousands, hundreds of thousands of dollars, and they're trying to figure out how is this going to help us. You're not actually receiving anything other than maybe a report, whether it's a PDF copy or a hard book, and then stickers on your equipment telling you what kind of clothing you need to wear. But really what it boils down to is because of the risk associated with an arc flash, it's really giving you the peace of mind that, or whoever's responsible for that vessel, it's giving them the peace of mind that they've done everything they could to protect anybody working on their equipment, whether it's the employees or contractors. So the consequences of not adhering to the arc flash standard, I don't know why the slide is like that, so I apologize, but the wide range of consequences for noncompliance includes the OSHA fines, the loss of productivity, you know, people being killed, people being injured. You know, it's arc flash calculations and, you know, protecting yourself from an arc flash or arc blast is really, what it really boils down to is protecting the people. You know, protecting the equipment and all the guts of the equipment is also important, but that comes secondary to the person that's actually working on the equipment. So always remember, people come first, regardless of how expensive that piece of tool or you know that electrical equipment is. If we could go down a little bit further, I think we're actually missing some of the questions here. Okay, there we go. Yes. So putting labels on, some people think that after we give them the stickers, that once they put the labels on, that their job is done. You know, whether it's the vessel owner or, you know, the building management team, their job is not done. They have to update those studies every 5 years, and it's still there. They still have to do their job and make sure that anybody working on their equipment is actually trained to, you know, wear that PPE and work on that equipment, regardless if the stickers are out there. Another question is, am I required to have my employees trained in arc flash risk? Well, anybody working within those boundaries, absolutely. If you are going to be working in those boundaries, best thing to do, especially once you expose the live energized parts within that equipment, is put a barricade so that anybody walking by doesn't just accidentally walk in, and if a fault happens to occur right when they're walking in there, that they don't accidentally get injured, because if you're the one working in there, you should be wearing the PPE, but an innocent bystander might not be wearing that same level of clothing, much less polyester clothing.
Repairs are underway because you're talking about approach boundaries that you have possibility of touching live circuits, is that what you're saying?
Well, it's not just touching live circuits.
There's electrical power everywhere.
That's correct, but it's actually the exposure to the live energized parts is where this comes into play. By some of those videos, you could see that as large as some of those blasts are, just because the equipment doors or dead fronts are bolted in place or locked in place, doesn't necessarily mean that the blast is going to be contained. They do actually manufacture arc resistant equipment. All that's doing is actually channeling that arc blast in a different direction, away from the maintenance personnel. But if that door happens to be open when that blast occurs, and they're doing maintenance on a particular section of, you know, arc resistant switchgear, without all those bolts in place, that protection from that arc blast is no longer there. And then for those that are actually interested in how long it takes to perform an arc flash study, once we have all of the information of the system, generators, motors, and this is all nameplate data, cables, transformers, once we have all that data entered in, it typically takes another 2 to 3 weeks to finalize the studies. But the largest amount of time is spent in modeling the system and making sure that you have all the details correct. Because if I make a mistake and I model the system incorrectly, or I don't model all the motors in there, I don't model all the generators, or different scenarios that can the system can be in, which means I'm not considering all the different amounts of fault current that can exist, then I don't want to basically end up in court where the lawyer could change, what I'm saying in the report and say that I didn't do a full analysis. So, just because once we built the model, there's still a lot of analysis and trying to determine why we're getting these levels at each piece of equipment. So 2 to 3 weeks after the system has been modeled is pretty standard. Now, if you're doing some of the largest facilities in the world, then could be a couple months. So,
what's your end result? Does it tell you where you have the highest potential of an arc flash?
It does
Or
actually.
all the places are that you have the potential?
Basically, any piece of electrical equipment, whether it be a panel board, switchboard, switch gear, disconnect switch, VFD disconnect, we label all of those. If somebody can peek inside that piece of equipment while it's live, then we're going to put a sticker on there.
If they can open it while it's live?
Mm-hmm.
Okay.
But even if they can't, let's say you had an interlock and you open the door and that limit switch somehow, cut the system off.
Be open before you can open it.
If you had one of those, we'd still end up labeling that equipment. It's just, everybody should be used to looking for those arc flash stickers, regardless if, the equipment, can be opened while it's, live or not be opened. So everybody should be used to looking for those stickers. So one of the problems that we normally face after 5 years and we go into a facility is that, while they're doing their turnarounds, there's people in there painting. And one of the things that they're painting over is the arc flash stickers. So yeah, you're typically painting the large pieces of equipment, and that's typically the equipment that can't be shut down. So maybe, if they're working at the main switch gear, right? That's typically where you're going to see the guys painting. But if something ever happened where they needed to do maintenance on a 5 kV, 15 kV, 35 kV circuit breaker, it's painting over those stickers just is basically posing a hazard to everybody. So we make it to where you're always looking for it, always. I'm not going to read all of these, but this is kind of beating upon what I was saying earlier about NFPA 70 or 70E and how it relates to OSHA, because a lot of people read those standards sometimes and they're trying to find wiggle words or ways out of actually performing the study. But I'll read the 4 bullets up at the top, or the 3 bullets, just so we could all, I guess, come into agreement about this. But the NFPA 70E is basically a national consensus standard, and it's a comprehensive standard that contains all the detailed information on how to protect the workers from the hazards of an arc flash. Employers must consider and adopt 70E when employees work on the electrical system. NFPA 70E is not an OSHA requirement, but that does not matter. OSHA requires employers to protect employees from electrical hazards. And although it's not, so with that second bullet point, not necessarily being a requirement, they do adopt the verbiage from the 70E. So OSHA issues citations based on requirements of the 70E through the agency regulations. And then if anybody wants to dig deeper into what OSHA is actually, requiring, then I listed all the OSHA, well, not all, but some of the most referenced portions of the standard there. So I'm not going to beat up too much more than that. I think that's it for the slides, right? So are there any questions that anybody has? Or can come up with.
What certification do you need to be a qualified person?
One of the first steps is actually you would do during the permitting process. Well, that'd be right before you work on the electrical equipment, right? But in order to do that permit process, you'd also have to already be trained in working on that equipment, right? Know how it was installed, know how to maintain that equipment, and what hazards are actually, present when opening that equipment up while it's live. So the safest practice is always to de-energize the equipment. There's really no way around, being safer than that. So, and just because a lot of people think that just because you turn off the main breaker on a panel board, right, that doesn't render you safe. If you have a local main on a panel board or whatever piece of equipment it is that you're working on, a lot of the higher arc flash incident energies that we calculate are typically at the incoming lugs of that lineup. So even though you turned off that main, if an arc flash happens to occur, and it could occur from dirt and debris or a rodent getting in there, somehow that arc flash occurs, you had that breaker off, but now you're exposed to that line side incident energy, and you don't have the protection of that main breaker, because the only equipment and personnel that are protected with that breaker being off is anybody working on the lower sections of that. But at that main section, you still have those live incoming conductors. So just be mindful of that also. Any other questions? No?
As far as like testing, measuring, and troubleshooting, the equipment has to be live when you're doing that, correct?
Yes.
Okay, so in that situation, until that zero energy state is verified through that testing, measuring, or troubleshooting, the PPE requirements based on that arc flash analysis would still be required.
Oh, absolutely.
Correct. Okay.
Absolutely. And there's another personal view that I have, but the 7DE also states that people doing a task such as infrared testing, you have to do that while the equipment's live. And de-energizing the equipment right before you're about to do that infrared testing kind of negates the whole infrared test, because you want to see what the actual load is on the system and see how hot those points are, on that piece of equipment that you're infrared testing. So although the 7DE allows it, it's just one of those things that you still have to be suited up, but even if the hazards are greater than what I consider to be the safest amount of 40 cals, they do permit it. So, yes, sir.
Is there a certifying body that would certify me if I wanted to do this work? You said certified, so that means somebody has to certify me, right?
Well, trained.
Well, I've been at this course today, and am I trained now?
No. It would have to be, it'd have to be basically a formally documented process, within your own, company, right? That says that, yes, you have been trained how to work on this particular type of equipment.
But there would be a company specific.
And it even goes as far as somebody changing out receptacles, because anything 50 volts or higher must be included in the arc flash calculations. But we don't actually model that, in our study models. But basically, battery systems, 125 volt DC battery systems that you find a lot of, UPS systems, those are actually required to have arc flash stickers on those too.
When you do I'm assuming it's a new facility or a new piece of gear, something you're doing an arc flash analysis, risk analysis. At what point does, with the exception of doing a major overhaul, does a management of change require you to redo it for that, either that piece of gear or the whole place?
Every 5 years at a minimum. But as substantial loads are changing in your system, you know, you add another generator. Maybe the utility company changed the transformer, or the fault current from the substation that's a mile away. You know, maybe they increase their capacity, and there's, you know, there's a lot of things that could change the amount of fault current coming into the facility. But within your facility alone, if you make major changes like increasing your chiller sizes, which you know is the larger motors have a larger contribution back during fault conditions. You know, those are all elements of change in the system that would necessitate you know, reviewing the arc flash study.
So it'd be other than in-kind changes for a MOC?
Come again?
So in MOC you have, when you make a change,
Mhm.
you have other than in-kind changes, which are change, you're making a change that's exact, whether you're making a change exactly with the same piece of equipment, same everything about it.
Yes. Well,
Or it depends on
that's
the
why
type of specific equipment.
it helps to have somebody review it. You know, if you're just changing out a light switch or receptacle, no, because there's really not enough fault current available at those terminals to sustain an arc flash. But when you're changing large motors, generators, transformers, then yes. Anything that could substantially affect the amount of fault current that you have, you know, within a system. Changing out static loads, that's not really going to affect you, like lights, you know, plug-in receptacles. That's not going to affect the study.
You mentioned regenerative loads characterising the models. Have you had much luck in modelling capacitor fed systems, so at the front end, power electronics feeding back into the fault?
Mhm.
Is there much? There's not a lot of modelling practices around that.
For what kind of?
So if you're feeding a a propulsion drive on a
Yep,
vessel,
yep.
then especially if it's active front end, when you have a short circuit on the main bus, that active front end is going to drive fault current from and obviously take out all the power from the capacitor. So, but it's often in most of these studies it's not included. The motive regenerative is, but the capacitor throughput is not.
When we're working with drives, we don't. The drives operate so quickly whenever there's actually, you know, a fault, right? So the contribution back from, you know, the motors on the load side of those drives is almost nothing. So we don't actually even consider any. Well, we still model it for basically making sure that the model is exact, but we actually turn off the regenerative fault current back from anything fed by a drive.
Okay.
So,
Thank you.
thank you.